So once again, welcome back all for this second day of this 3 days online workshop on design of experiments and engineering perspective. Yeah, warm welcome. So today, in the first session, we are going to look into some of the basics of response surface methodology and some hands-on training using Design Expert software. In the afternoon session, we are going to look into some of the basics of analysis of variance, these formulas associated with that, and how we are going to formulate a ANOVA table. So this session is basically about the response surface methodology, which is particularly useful for multivariate analysis or multi-response optimization technique. So this RSM is a specialized DOI technique. So this also comes under the design of experiments. But the difference between Taguchi's approach and RSM is, in order to avoid experimental errors, more number of experiments will be incorporated in this RSM design. Apart from that, some repetition of experiments is also possible with this. So the amount of error that exists between the experiments can be curtailed down. So this RSM is a combination of both the optimization as well as statistical methods, which is specifically useful to model and to optimize designs. So when compared to that of Taguchi, these RSM designs will provide us with a empirical models for the output responses that we are going to select. At the same time, this RSM is specifically useful for multi-objective optimization. The multi-objective optimization is optimizing more than one response simultaneously. For example, consider two outputs, surface roughness and material removal rate. The surface roughness and material removal rates are of different objectives. Surface roughness should be as minimum as possible, so it comes under the minimization, whereas the material removal rate should be as maximum as possible, so it comes under maximization. When combining these two, a conflict of interest exists. So this RSM is specifically useful in removing these things, the hurdles, so that a multi-objective optimization is possible. Here we are going to use a tool known as desirability analysis, which provides this multi-objective optimization approach. So with this introduction, we'll move on to the response surface methodology. So as told, a specialized design of experiment approach is this response surface method. We normally call it as RSM. So in this, we are going to combine both the statistical tools along with the optimization methods so that a multi-objective optimization can be done along with some empirical modeling. Here we are going to develop models. Based on that models only, we are going to optimize the initial design. For empirical designs, we are going to use regression analysis. So that regression analysis is inbuilt in the software. So automatically when we are going to analyze an output, it will provide us with the regression modeling that we normally call as the empirical models. While designing the experiments, we should be very careful, because we are going to select how the output is related to the input. whether we are going to consider only the main effects or we are going to consider the interaction effects or we are going to consider the square terms, similarly like this. So how we are going to analyze the data? So we have to be very careful in this. So let us see an example. A chemical engineer needs to find the values of two inputs, temperature and pressure, that will produce a maximum yield of a process. The process may be any chemical reactions or something. So that we are going to model in terms of y is equal to f of x1 comma x2 plus eta, where y is my output, that is the yield, where x1 and x2 are the inputs and f comprises the function. Then epsilon represents the noise or the error that is observed in the response. So this is like equating the input on the output by means of a model. So as told, this response surface methodology produces some response surfaces from which we are going to interpret the behavior. So the surface is being represented by means of this modeled function. Okay, that is called as the response surfaces. So all these things, the optimization, the formulation of response surfaces, everything depends upon the model that we are going to develop. So that's why we should be very careful in what type of model that we are going to choose during the analysis procedure. So these are the some of the response surfaces that is being produced during the analysis. So this is a surface plot, which is nothing but a three-dimensional plot in which we have two inputs and an output. The inputs that we are considering in the previous example is the temperature, that is x1, and the pressure, that is x2. So these two are related with that of the yield. So a response surface is produced in the first example. So this is a maximization curve, because since we are going with the maximization, the curve is like an umbrella. So this curve is called as a maximization curve. So we'll see what is minimization curves and all in the latter part of this presentation. In the second example, we can see a contour plot. So the contour plot and the response surface plot are integrated in the same plot. So what is the difference between a contour plot and a surface plot? The surface plot is a three-dimensional plot, whereas the contour plot is a two-dimensional plot. So that's the difference. Apart from this, there is no difference at all. So the surface plot is a three-dimensional plot, whereas the contour plot is a two-dimensional plot that is drawn between the relation between two inputs and then outputs. So what is the first step? The first step in the response surface methodology is to find a suitable approximation, so that the true relationship that exists between the output y and the set of independent variables. The independent variables are nothing but the inputs that we are going to select. That is, y is equal to f of x1 comma x2. So a suitable approximation that we are going to find, so that a true relationship exists between the inputs and the outputs. So normally we have low order polynomial and higher order polynomial. It depends upon the problem that we are going to choose. So this selection is very important during the analysis procedure. So initially, if I am going to consider only the main effects, then a linear relationship exists between the inputs and the outputs. The inputs are the independent variables, whereas the output is the dependent variable. So a linear is nothing but In this equation, we can see y is equal to beta naught plus beta 1 x1. So where beta naught is a coefficient, a constant, but beta 1 is the coefficient that relates with the parameter 1. Similarly, beta 2 is the coefficient that relates to parameter 2. And finally, there will be some error that should also be calculated. Okay, so this is a linear model because we are not going to consider any interactions or square terms. If there is any curvatures, if there is any non-linearity, then the polynomial of higher degree has to be used. So as told, so we have to choose whether we are going with a lower order polynomial or higher order polynomial. It mainly depends upon the relationship that exists. Whether it is a linear relationship, then I can go with a lower order polynomial. But if there is any curvature in the system or the model, then a higher degree polynomial should be used. That may be a second order. In this case, here you can see y is equal to beta naught. The beta naught is nothing but the constant, and eta is the error, epsilon is the error, so that is constant. But in between, we can have the xi is nothing but the input variable, and xi square is the square term of the input variable, and xi xj is the interaction effect. In the case of the chemical process, we have considered temperature and pressure for yield. So I'll frame an equation here. So y is equal to beta naught plus beta 1 temperature plus beta 2 pressure plus beta 3 into temperature into pressure, that is xi xj. Xi is temperature and xj is pressure. So temperature into pressure plus beta 4 temperature square plus beta 5 pressure square. We are also going to include the square terms also plus the error term. While approximating the polynomials, whether it may be a lower order polynomial or a higher order polynomial, the methods of least squares is normally used for estimating the parameters. By fitting the surface, this analysis is being carried out. The model is fitted into a surface. Thereby, the further analysis is being taken away. So, the designs or the models that is used for fitting response surfaces are generally known as response surface designs. So, this figure shows you the sequential nature of the response surface methodology. So the ultimate aim of any optimization procedure is to identify the ideal conditions or the optimal conditions. The ideal and optimal are one and the same. The ideal conditions, so that we have to maximize the yield or minimize some of the ill effects. So maximization or minimization. So we are going to focus only towards our objective. So in this case, we have a design space. This we call it as a design space. In the design space, presently we are something apart. Right? From there, we have to move towards the region of optimization. We have to move towards the region of optimization, thereby improving our path. The path improvement is performed by developing a suitable model. So whether we are going with a linear model or a second order model, that depends upon your problem selection, the number of experiments that is being used, and while doing the hands-on training, I will tell you how to choose all these things. So the main aim is to move towards the region of optimization, that is the optimal conditions within the design space. This is what we call it as a design space. The range of values that we are going to select for analysis is the design space. because we are going to search, we are going to search the solution within that range only. So that range of values that we have selected, that is a low level value and high level value, and that is known as the range. So we are going to find out the optimum condition within that decision space. So we are at a particular position now, and we are going to move towards the region of optimum condition. So initially, we will be in a position that we are far away from the optimum conditions. We are far away from the optimum conditions. So in order to move towards the optimum conditions, there are two methods we will normally utilize. One is the steepest ascent and the other one is the steepest descent, because we have to move rapidly towards the position of optimum conditions, that is called as convergence. Okay, so we have two objectives. One is to maximize a response or to minimize a response. When to use steepest ascent and when to use steepest descent. If I am going for a maximization problem, then we have to use steepest ascent. Ascent means increasing. So the steepest ascent is the procedure to move in a sequential manner towards the direction of response by increasing. On the contrary, for minimization problems, we should use the steepest descent. That is moving sequentially in the direction of minimum or the maximum decrease in the response. Now, how much response that we are going to decrease? For example, take a surface roughness. The surface roughness value should be as minimum as possible. So we have to move towards the maximum decrease in the response. So maximum decrease in the response, so that is known as steepest descent. So this is the one. So initially we are at some position, that is we are far away from the optimum condition. So depending upon our objective of maximization or minimization, we have to choose whether we have to use steepest ascent or steepest descent. For maximization, I am going to increase. So here you can see the y bar is 10. At present, we are in y bar 20. Since we are moving towards the steepest ascent, that is maximization problems, the y bar tends to increase. That is the y bar is the mean, the mean value. So here you can see the two inputs, x1 and x2. While in the case of steepest descent, this is the reverse case. If I am going to be in y bar 40, then I have to move towards y bar 0. That is, I am going to move in the reverse direction, that of the steepest ascent. So, first of all, fix your objective. What response that we are going to choose, and whether we have to improve that, that is, we have to maximize that, or we have to minimize that we have to finalize, and then we can move further in this analysis. So here we will come across a point that is called a saddle point or a stationary point. The ultimate aim of this response surface methodology is to identify the optimal conditions. The optimal conditions is nothing but a value between the range of the input parameter. So we have to find the levels of x1, x2. x1, x2 and xk are nothing but the input parameter values that optimize the predicted response. If the partial derivative is 0, then the point is known as the stationary point. So the stationary point that represents a point of maximum response, then it is called as a saddle point. Whether it is a maximum response or a minimum response. The maximum response is the yield. The minimum response may be the surface roughness, then it is called as a saddle point. So we should know the terms. Stationary point is when the partial derivative of the ideal conditions is 0, then it is a stationary point. When the stationary point represents a maximum response or a point of minimum response, then it is called as a saddle point. So during analysis, depending upon the model that I am going to develop, the model will be fitted onto a response surface. So once again I am telling, we are speaking about the model. So what type of model that we are going to develop, whether it is a linear model, that is low polynomial model, or higher polynomial model. So depending upon the model that we are going to fit, we'll come across different response surfaces. So this response surface is a surface with maximum, that is maximization. So how we are going to obtain this? Okay, it mainly depends on the fitted model. So similarly, this is the surface with minimum. So here we can have a concave surface, So look at the shape of the contour plots. So here you can see it is in the upper side. The contours are open to the upper side. Here the contours are open to the lower side. So that we can also identify. So there exists a condition where both the maximum and minimum exist. For example, if I am going to increase the temperature, after some temperature, the yield will tend to reduce. After certain temperature, the yield will tend to reduce. So it reaches a maximum and then it tends to lower. So that term is known as min-max. That is a combination of both the maximum and minimum surfaces. That is included in this fitted model, and that is called as the min-max, which is a saddle point. So here you can see the surfaces, the contour plot. The contour plot, that is the superimposition of the maximum contour and the minimum contour. So from this we can identify that a saddle point exists. So there are different designs in RSM. So normally we will have two specific designs. One is box Benton design and the other one is the central composite design. The difference is, in this we have to provide only the lower and the upper limit. No intermediate limit will be provided. But in the case of Taguchi, if I am going to consider 3 levels or 4 levels or 5 levels, for each level I have to select or I have to provide the level values. But in the case of RSM, we have to provide only the lower and the upper limit values for the input parameters. The intermediate values will be taken care by the system itself. So how it is going to have? So first look into the box Benton method. The box Benton method consists of, so this we represent as a cube. So that is called as the center point, axle points. No edge points is there in the box Benton method. The -1 represents the lowest range and +1 represents the upper range. So the middle point represents the intermediate point. Here we can have, so for each and every edges, I have a middle point and a axial point for this cube, and the axial point for this cube are not for any side surface. But in contrary, a face-centered composite design, central composite design, we call it as CCD, central composite design. We can have the edges, then we have the center point for each and every surfaces, the front surface, top surface, side surface, bottom surface. We have the center point. Apart from the center point, we have the axial points. So when comparing to that of the Boss-Benham design, the number of experimental runs in central composite design will be higher. The number of experimental runs in central composite design will be higher when compared to that of Box-Benham design. So in Box-Benham design, we will have a value that is called as alpha. So depending upon the value of the alpha, it is whether it may be a face center or rotatable designs. There are many designs like that. During the hands-on training, I will tell you all these things. Okay. So this is the factorial designs with the center points, with the axial points, that is specifically to the central composite design. In the first one, we have the center points, that is on the edges and the center of each and every side. For example, take a front side. The four corner, we have a point. The points are nothing but the values, and the center point of that surface. We are going to consider this as a value. Then apart from this, we will also have the axial points, the axis that pass through the cube. So by combining these two, we will have the central composite design. So while going on to the hands-on training, I will tell you each and every how to change. This can also be changed according to our needs. So in the case of RSM, there is an important term that is called as rotatability. So how we are going to obtain the surface design that is decided based on this rotatability. So the purpose of the RSM is to find the location of the optimal conditions in a precise estimation in all the directions, because we should not move in a single direction, but we have to go throughout the design space to identify the optimal condition, whether it may be a steepest ascent or it may be a steepest descent. But within the design space, we have to move towards all the directions, not only a particular direction. That's why this rotatability is very much important. So a central composite design is rotatable by means of using this alpha value. So that's why I told you earlier. In a face center value, we take alpha is equal to 1. So the rotatability is 1. So we can also change 1.4 or 2 or whatever it may be. Depending upon the number of ranges that we require, we can change the alpha values. So the value of alpha that we are going to select for the rotatability of the response surface design is mainly depends on the number of points in the factorial portion of the design. So this RSM is also one of the factorial designs, but we can change, that is, we can increase or decrease the number of experimental by changing these axial points and center points. That we can see in the hands-on training. So depending on the number of points that used in the factorial portion of the design, the alpha values can be changed so that the rotatability of the surface design can be made. So the number of points that is used for design in the factorial portion, because it has the factorial portion centers axial points. So by changing the alpha values, the factorial design positions can be changed. Okay. The spherical CCD, coming on to the spherical CCD. So rotatability is normally a spherical property, because a spherical means we are going to search towards the total design space. But in the case of center runs, the choice of alpha makes particularly important because I can take any values. I can take any values for alpha, and depending upon that, I am going to design the central composite design. So there are 3 to 5 center points that can also be reduced by varying the alpha values. Apart from that, how many center points that we are going to choose? If I am going to choose more number of center points, then in all directions the optimal conditions will be searched. If I am going to reduce, then we are going to narrow down this search. Then comes the box Benton design, which is the simplified version, because whatever the range that we give, that is the low value and high value, automatically it takes the middle value. That is, normally the alpha value is going to be 1 in this case. So what are the different types of 3D surfaces that are fitted in response surface methodology? So normally we have a linear or a planar surface, a plane surface. That is, with the change in one variable, the output varies in a linear way. The output varies in a linear way. In the second case, it is the quadratic surface. That is, with the increase in one input variable, the output varies in a parabolic way. The output varies in a parabolic way, that is in a non-linear manner. Similarly, with change in the next parameter also, so kindly look the second image. If the change in x1, a non-linear change in y is observed, and also with change in x2, a non-linear change in y is also obtained. Then we come on to the ridge surface. With the change in one variable, a linear change in output is obtained, whereas with the change in the next variable, a non-linear change in output is obtained. So this is a ridge surface. Then a saddle surface. A saddle surface is nothing but a min-max condition. So in previous itself we have seen a saddle point is nothing but a combination of both maximum and minimum. That is, up to a certain point it may be maximum, then it tends to get reduced, or up to some point it will be minimum, and after some point it tends to increase. So in the condition, in the fourth image, we can see the curvilinear tends to decrease initially, and after some point it tends to increase. So first minimum and then it tends to maximize. So that is called as min-max condition. Then comes the twisted surface. The twisted surface occurs because of the variations that exist. So this is also of particular importance during the study. So by using these different surfaces, we are going to interpret the different surfaces that we are going to obtain during the analysis in RSM. Then coming on to the desirability function, the main purpose of going with response surface methodology is it is specifically useful in multi-objective optimization. The multi-objective optimization is performed in RSM by means of this desirability approach. The desirability value, the ideal desirability value is 1. The ideal desirability value is 1. That is, it indicates higher overall satisfaction of all the responses. The responses may be 2, 3, 4 or 5, whatever it may be. By increasing the number of outputs, the desirability value tends to lower, because each and every outputs has its own effects. So by increasing the number of outputs, the desirability value tends to lower. So don't get worried about that. But the ideal value of desirability is 1. The desirability value ranges in between 0 to 1. So 0 is the most undesirable values, whereas the values that are nearer to 1 is the most desirable values. By getting a desirability value nearer to 1, a greater total fulfillment of all outputs can be obtained. That is, a very good fitted model is possible. So depending upon the desirability. So here you can see In the case of maximization of the yield, for example, YA is the yield, we are going to move towards the disability value of 1. So DI, so we are going to move towards the disability value of I in between the ranges, lower and the upper limit. LI is the lower limit and UA is the upper limit, and then we are in between that we are going to obtain the disability value for larger the better condition, that is improving the yield. Here comes the lower the better condition. For example, consider a surface roughness. The surface roughness has to be as low as possible. So from the upper limit, the ideal conditions moves towards the lower limit. But in the previous condition, you can see from the lower limit it moves towards the upper limit because it is a desirable one. That is, the larger the better. So the value should be nearer to the upper limit. But in the case of surface roughness, the values should be closer to the lower limit. That's why we have to move towards this condition, from upper limit towards the lower limit. So this is the nominal the better. The nominal the better is nothing but a target value. Here comes the constraint conditions. The target is nothing but a constraint. I am going to provide some constraint. That is, the surface value should be this much. So I am going to fix a target. It should not be lower than this or it should not be higher than this. For example, take it as 4 microns. I am going to fix that constraint as 4 microns. So what is the optimum condition for that? So one parameter I am going to fix it as constraint, that is target, while the other parameters can be lower or higher. In turning operation, we are going to construct 3 outputs: flank wear, surface roughness and material removal rate. The flank wear should be the lower the better. The material removal rate should be higher the better. Now the surface roughness I am going to set it as a target. So during the hands-on training, I will tell this. Okay. So I am going to set it to a target value. So I am going to make all these things and I am going to find out a optimum condition. That is also possible in this. Again, a major difference between Taguchi's approach and response surface approach is Taguchi design provides the optimal condition within the selected level values. If I am going to consider 100, 200, 300 for cutting speed, it will give us whether 100 is best, 200 is best or 300 is best. But what happens when the optimum condition is in between 100 to 200? For example, if it is 180, the optimal cutting speed is 180. What happens? No, it will give only 200 as the optimum condition. But in the case of response surface methodology, the exact optimal condition within that range, whether it may be 180 or 183 or 179, the exact optimal condition is possible with the response surface methodology. So that's why it is more advantageous. So these are the values. These are the values that we normally use. These are the formulas that we normally use for determining the disability value. So as told, the disability value ranges between 0 to 1, where 0 is the most undesirable value and 1 is the most desirable value. So a value that is nearer to 1 is a perfect one. So f(x) is nothing but the function. Okay, a and b are the limit values and r is the number of desirability functions. The r here, if I am going to consider flank wear, surface roughness and material removal rate, then r is equal to 3. So that is for the overall disability. dr max is the disability function for material removal rate. dr minimum is the disability value for flank wear and surface roughness, because these two are minimization problems. But when combining all these three, the total disability D is nothing but the pi r to r is equal to 1 to r. R is nothing but the number of outputs. Here the number of outputs is 3 into the disability value of each and every individual outputs. So based on this, we are going to provide. So what are the various plots that is associated in RSM? So first one is the normal probability plot. So the normal probability plot indicates whether the residuals follows a normal distribution or not. Because whatever in statistics, we are more concerned about the normal distribution. So the residuals, that is the difference between the experimental and the predictor outputs, is the residuals. So these residuals should follow a normal distribution. The normal distribution is possible when a straight line is fitted. So from this, we can easily identify whether the residuals are normally distributed or not. If it is not normally distributed, then once again we have to do that specific experiment and then we have to fit. The residuals versus run plot for each and every experiment. For example, if I am going to perform 20 experiments, for each and every experimental trial, a residual will be there. That is the difference between the experimental and the predicted. How this is predicted? An empirical model is developed using regression model. By using that empirical model, we are going to predict the output for a given input. So I know the experimental values. By using the regression models, I am going to predict, and the difference provides the residuals. For each and every experiment, how much is the residuals? Whether it is higher or lower or within the nominal range. So a upper limit and a lower limit will be formed automatically, and if the residuals are within that lower and upper limit, then it is good. Also, the plot should be randomly scattered. The plot should be randomly scattered. If it is not randomly scattered, then blocking and randomization will improve the plot. So that's why we have gone. So previously we have seen randomization, replication and blocking. That's why we are more specific about randomization, replications and blocking. These three principles are specifically useful in order to improve the analysis procedure. Then predicted versus actual plot. So what is my predicted value? What is my actual value? That I am going to plot. Thereby we can identify how close the prediction is possible with the developed model. So how we are going to improve the developed model? We have a lower polynomial and we have a higher polynomial. In the lower polynomial, if the prediction is not close enough, that is, the difference between the predicted and the experimental values are higher, then move towards a higher polynomial, so that the closeness of the experimental and the predicted value is possible. So these are some of the examples. So this is the first one is the normal plot of residuals. So this normal plot of residuals are normally distributed so that a straight line fit is possible. And second one is the residual versus run plot. In the residual versus run plot, a upper limit and a lower limit will be formed, and for each and every experiments, in this case 30 experiments were performed. You can see in the first experimental trial what is the error and how it is being varied. So the maximum comes under for 8th and 10th experiment, a higher, and also for 20th experiment. So a large variation is observed. So that also we can interpret. So then comes the predicted versus actual plot. So what is the difference between the actual and the predicted? So there are 30 experiments, so 30 points will be there. So 30 points will be there. So these should be fitted through a 45-degree straight line. So these 2 points should be scattered uniformly over that 45-degree straight line. The red point indicates that the prediction is not that much accurate. While clicking that point, we can identify which experimental run it is. By clicking each and every point, there are 30 experimental runs in this case. So by clicking each and every point, the experimental number that corresponds to that we can identify. Then comes the perturbation plot. The perturbation plot shows a variation of all the inputs that we have studied, that we have selected for analysis in the experiment. So in this case, in this example, COD is the output, chemical oxygen demand, that is the output, and we have considered 4 inputs: input A, input B, input C, and input D. So input A varies from lower level to higher level. -1 is the lower level value and +1 is the higher level value. So it tends to decrease. Okay, that is when the parameter A increases, the chemical oxygen demand tends to decrease. But here in the case of B, C and D, we can see after some point, initially when I am going to improve the value, the COD tends to increase. After a particular point, it tends to decrease. That is min-max condition. It comes across the min-max condition. The point at which all the four coincides is the maximum condition. Is the maximum condition and the ideal condition. So from this we can identify the things. So the perturbation plot helps us to compare the effects of all the selected input parameters in the design space. So how it varies for a particular output. So how this is drawn? If I am going to consider the parameter A, the other 3 parameters B, C and D should be kept constant value. If I am going to vary B, A, C and D should be kept at a constant value. So only one factor should be changed while the other factors should be kept constant. So one factor plot. Then we come on to the one factor plot. The one factor plot shows the change of output by changing a single factor. How the output changes by changing the value of the selected input. So the first one. So here you can see the black. The black is my solid concentration. The solid concentration varies between 5 and 15. So when I am going to consider the solid concentration as 5, the COD is higher, but when I am going to increase that towards 15, the COD tends to reduce. The COD tends to reduce, but whatever it may be, a slight decrease or something, it tends to decrease. Similarly, here in the next plot, we can see the interaction plot. The interaction plot is, I am going to consider 2 input parameters. In these conditions, I am going to take solid concentration as well as pH. So this is a anaerobic digestion process. Anaerobic digestion process. So we have considered solid concentration and pH. So what is the effect of, that is the combined effect of solid concentration and pH over the chemical oxygen demand? That is also be possible with this. So we have to make perfect interpretation from these graphs. Then the contour plot. The contour plot is nothing but a 2-dimensional plot that is drawn between 2 input variables and the output variable. So x, y, z. X and y are inputs and z is my output, but this is drawn in a 2-dimensional manner. So the first image is the contour plot. So it is drawn between the solid concentration and pH. for the chemical biogas production. It is for the biogas production. So here you can see the different values, different values. So starting, so when the solid concentration is in the middle value for cell, for example, in the value of 9 and pH is in the value of 7, higher biogas is produced because the value is 6300. Once we deviate from this, the value tends to reduce. The biogas production tends to reduce to 6250, 6200, 6150, 6100. That is, with the lower values of pH and higher values of concentration, the biogas production will be lower. Or with the lower solid concentration and higher pH also, the biogas production is lower. But with a moderate value of pH and solid concentration, the biogas production is higher. So biogas production has to be maximized here. So the surface plot. The next plot, we are going to see the surface plot. So along with the contour plot. The surface plot is a three-dimensional plot that is drawn between two inputs and an output. The inputs that we have considered is pH and co-digestion. pH and co-digestion, and the output is chemical oxygen demand. So from this we are going to interpret. Okay, the COD should be maximum, so we have obtained a maximization curve. So then we come across the Q plot. So the Q plot shows the predicted values for any outputs, the predicted values of any outputs based on the input parameters selected, selected for any three factors, So this is it. So this is drawn for three factors. That is A, solid concentration, B, pH, C, co-digestion, and the output is chemical oxygen demand. So the predicted values is possible. So in the front surface, the x-axis is pH and the y-axis is co-digestion. The pH varies between 5 to 9, and on the right side view we can see the solid concentration that varies between 5 to 15, whereas the co-digestion increases from 0 to 40%. So different combinations of these three parameters, solid concentration, pH and co-digestion, what is the chemical oxygen demand? So that are the values that is given in 24.908, 29.3452, 25 on each and every edges. We can clearly identify that. Okay. So this Q plot is specifically useful for prediction purposes. Then we come across the ramp plot. The ramp plot and the disability plot will be obtained during the multi-objective optimization. So far what we have drawn is diagnostic plots and model graphs. Okay, so the previous plots are called as diagnostic plots and model plots. And now we are going to enter into the multi-objective optimization by using disability analysis. During disability analysis, our ultimate aim is to identify a optimal or a ideal condition for the selected inputs over the obtained outputs. So here this is a ramp plot. Here we can see I have selected 4 inputs: A, solid concentration, B, pH, C, temperature, and D, co-digestion. These are all the inputs. And 2 outputs I have considered: biogas production and chemical oxygen demand. In this case, my aim is to increase or maximize the biogas production and to maximize the chemical oxygen demand. So this ramp plot, for example, take the solid concentration. Only the lower and the upper limit will be provided. The optimal condition obtained is 7.38, which is denoted by the red dot. The blue dot represents the output, whereas the red dot denotes the input optimal conditions. So In this case, it is very clear that in between the range, whatever optimum condition that will be displayed. But in the case of Taguchi, only the selected level values will be considered as the optimal condition. Any one of the level values will be considered as the optimal condition. So in between, if there is any optimal condition, that will be displayed in this response surface methodology. So by using this RAM plot, we can identify the optimal input conditions and also the predicted outputs. The output is also predicted, the output is also predicted for the optimal conditions. That is also given here. The biogas product, the predicted biogas production is 6343.67 and the predicted COD is 37.67. Here you can see the graph is inclined from lower to higher. So that is the steepest ascent because I am going to move towards the optimal condition in a for maximization condition. So that is the steepest ascent. Similarly for COD also a steepest ascent is visible. So this is the disability plot. So the input disability values are normally taken as 1. The red are the inputs and the blue are the outputs. The normal disability, the disability values for input conditions are normally taken as 1, whereas for output, the desired disability is 1. Because the disability ranges between 0 to 1, where 0 is for undesired value and 1 is for desired value. But the values that are closer to 1 is preferable for disability. For individual biogas production, the disability is 0.87, whereas for COD, the disability value is 0.99. So, by taking these averages, we can have the combined disability value of 0.93. So, from this, we can prove that with the combined disability value of 0.93, a perfect model is developed during the analysis. So this is all about some of the introductions of the response surface methodology. If any questions, you can chat with me for 5 minutes. After 5 minutes, sharply at 11 o'clock, I will start the hands-on training session. Thank you.